so stick to 2 dimensions. It's hard enough, really. And so we're doing linear algebra specifically right now. Linear algebra, all the linear operators, 4 numbers, nothing else. And the variety of things that can happen, you have to notice. So all the stretches that and this and flips that we've seen before, they are present in one dimensional case. And now, in addition, we have rotations and things like this, like shearing, which is even hard to describe without actually having a picture in front of you. Okay, so now with this variety of things that can happen, we want this is, by the way, the rotation by pi 2. Well, as you can see, I chose the circle instead of circle. I have ellipses there so that you can actually see the rotation. Okay, so what's the trick? And there is a very simple trick to actually build a linear operator based on its verbal description. So the idea is very simple. It is that to see where the basis vectors go. So where does 1, 0 and 0, 1 go? That's all the reds. Okay, so that's the most important thing to understand about linear operators is that fully determined by their value at the basis the standard basis vectors. Okay, so once again, and it literally what this on the right shows is wherever 1, 0 goes, that's the first column of your matrix, and wherever 0, 1 goes, that's the second column of your matrix, like this. Okay, so that's the illustration. So once again, all you need to know is where the basic vectors go, and then see where they are from the verbal description. You might be able to, and then just that produces those 4 numbers that you're looking for. That's all there is. That's really as simple as it seems. And that is important just when you build it, because it is, like I said, it's very simple. The problem that you're trying to solve, you have a description. How do I come up with a matrix? And that's how. But also on a kind of a more conceptual level, it is what a linear operator does is think about the meaning of a linear operator is as if you have your xy plane made of kind of wooden planks for the axes. Okay, and then so these are the planks. Okay, and then the rest is a kind of a stretchy fabric. Okay, and then what happens under a linear operator is that we control the planks only. Okay, so we do not move the fabric. The fabric moves with the planks. Okay, so we can take those 2 planks and do what we want with them. We can just rotate the whole thing together or separately. We can flip them naturally, but primarily you can also try, if it's not wooden, you can try to stretch them too. So which means that it's not really wooden as much as, I don't know what you can stretch, but basically, if whatever you have done with the planks, the fabric follows. Okay, so you don't need a control over the planks in order to produce something with the rest of the plane, and that's the restriction on what the linear operator does. Because it's linear, then we don't have to point out where every x goes. Okay, so if you know where the basis elements go, you know where the rest of them go. That's how linear operators are designed. Because everything is so if you ask why. The answer is because AB is equal to AI plus BJ. Okay, so in other words, wherever I and J go, okay, under your linear operator F. Okay, so then if B is unknown, then also wherever AB goes under F is also known. Okay, so that's just the thing about the linearity. Once again, ensures that we only need to know where the basis vectors go. So this is all is here. Okay, So, all right, so let's look at some of the examples. That's the theory. Once again, you go 0, 1 goes to AC, 1, 0 goes to 0 AC, 0, 1 goes to BD, and then that's we have our matrix there. So let's look at some of the, to confirm that, let's look at some of the familiar and less familiar linear operators. The zero operators, naturally, what happens? It's not that all vectors go to zero. You just look at where the basis vectors go. And so 0, 1, 0 goes to 0, okay, right here. And then 0, 1 goes to 0, 2. So you take these two columns, right here, and then combine them together into one matrix, and that's it. Okay, so the identity, which means that 1, 0 goes to 1, 0, 0, 1 goes to 0, 1. And so once again, take these two columns, these are the columns, and they're combined together, producing the matrix. That's okay. Horizontal stretch. Okay, so this one's still 0. The second column remains the same, but the first one is 2, 0. That's multiplication by 2. And so as we can see that is the new matrix is right here, 2, 0, 0, 1. Once again, split into two columns where they come from. Vertical stretch, I have 3 instead of here, so that's the effect on the matrix is in the second column. Horizontal flip. So nothing happens to the second column. That's why I have 0, 1 here. On the other hand, what happens to the first column? It is negative sign emerges. And so I just take this column right here and place it as the first column in my matrix. Okay. Vertical flip, flip about the diagonal. Well, 1, 0 becomes 0, 1, and 0, 1 becomes 1, 0. So that's how that matrix emerges. Once on the other diagonal, because what has happened there, just two columns have been interchanged. Okay, so so exercises. So literally just take the description and let's take this 56. So linear operator leaves the x-axis x-axis intact. Okay, what does that mean? It means that 1, 0 goes to 1, 0. Okay, so which means that in my matrix, the first column will be 1, 0, and the second one stretches the that description is not quite but okay. So stretches the I'm afraid this is just not a good example. So stretches the diagonal by a factor of 2. So you can't really have these two at the same time. So it's not really a good example. So let's take this one. This is one looks fake. So you have to somehow, no matter what the description is, you have to convert that description into the into the description of what happens to the axes. So if you know where the x's go and how, then you know where the basis vectors go. So this one, as I was saying, 1, 0 goes to 1, 0. And so under this linear operator A, and so in your matrix, the first column will be 1, 0. However, this stretches by a factor of 2, so 0, 1 becomes under A becomes 0, 2, and so that's how we put here 0, 2 over here, and that's how my matrix has been formed. Okay, so the rest is more and more complex, but most of the time we can sort it out. This is a good example of how it happens, how we produce something entirely non-trivial in that fashion, and that's the matrix of a rotation. So if alpha is your angle, then this is the matrix. So the proof is really not complicated, as you can see. You just look at a basic trigonometry. So if you take a 0, 1 vector, I'm sorry, 1, 0 vector, the horizontal one rotate to alpha degrees. Okay, so then you just look at the so this is literally this one right here is vector 1, 0. Okay, and then under the operator it goes right here. And what are its coordinates? Cosine alpha, sine alpha. So the new vector is literally cosine alpha, sine alpha. Okay, and similarly, we are doing the same thing, but we're doing it with the vertical vector. This vector is 0, 1. Okay, and under the transformation, where does it go? Once again, looking at the at the coordinates of the new vector. This is my new vector, okay, and that new vector, its coordinates are negative sine alpha, cosine alpha, and these are the columns. The columns. So even though I write them as a row, but these the columns, and so I made of these columns and make up my matrix. Okay.
So you're rotating whatever your original one was by alpha degrees counterclockwise.
Radians, yes.
Radians, right?
Yeah. Yeah. So let me. This is the rotation. So alpha. So yeah. I better have a direction pointed out very clearly. Rotation is. I mentioned it here. Rotation through alpha. Counterclockwise, the positive direction of the rotation. And so, but naturally, I could have negative rotation just as well. It will just go in the opposite direction. Still works out because, so you know trigonometry well, I presume. So you know that the sine and cosine are actually defined on the whole real line. So this is actually works. I could put alpha here, and it's true for each real alpha. Okay, so it will repeat itself naturally after 2 lines. Okay, so then the examples maybe of themselves are not very impressive, but we had the basic examples. We had the rotation, which we did not have, and then the trick is actually to do compositions. Okay, so for example, if I want to do rotation followed by stretch, I have the two functions described by matrices. And then that if I combine them properly, I could, but maybe later, that will give me the matrix for the whole transformation. So once again, multiply by 2 and rotate in some order. Either order works out the same well, same magnitude. Okay, rotation 45 degrees. So if you were to write it, I just plug in pi over 4 into my formula. It doesn't really matter in the table that produces this. It doesn't matter if this done is with Excel. You don't even need to know what the cosine pi over 4 is squared of 2 over 2. It makes no difference because the Excel will do the computation for you. And so you plug in this matrix, and this is the transformation that you see these stretched these ellipses. That as primary curves, they have been rotated. You can see very clearly the sides are exactly the same. They're still counterclockwise, so that's pure rotation. No stretching. That if you look at the colors very carefully, that's indeed what has happened. Okay, so rotation, stretch, shrink. Okay, so well, this one is just another example of you discover it appears to be a rotation in stretch shrink, and then from it you might be able to figure out what's happening. But most of the time, if you have nothing but a matrix, can you decompose it into more elementary transformations? That's a question for a different course, I suppose. So because basic transformations are stretching, rotating, and flipping. Okay, so hypothetically, you can decompose into every linear transformation in the composition of elementary transformation. Okay, so let's quick look back at the ODEs. What's that we have here? What we have ODE systems of ODEs right here. So that's what we used to have. That's a linear system of ODEs. X and Y are their rates of change of X and that of Y depend on X and Y separately. Once again, maybe populations that are either cooperating somewhat and also competing somewhat. And these populations actually could be positive and negative. That's so to be clear. And then now what we have done, now we have a different interpretation with vector interpretation. So we split it vertically. So then my derivative is not derivative of x and y, but rather derivative of x and y combined to a vector. X, y is also combined to a vector, and then the coefficients of my system ABCD are forming my matrix. Okay, so then this is the abbreviation that we have. this is the total abbreviation is here. So we have x, which is a parametric curve to be differentiated with respect to time, which is not present here, not visible rather. And the matrix ABCD is what actually determines the dynamics of our process, of whatever phenomenon we're looking at. If you write this side by side with the one-dimensional case, you can see how similar it is. So x, except lowercase x, I have uppercase x, and in the one-dimensional case, we have solution lined up, exponential. So it's not dissimilar. Once again, the solutions that we're going to produce for our system will be made of exponential functions. They combine in a more complex way, but nonetheless, it will be like I said, made of exponential functions. So this is like a building block for two-dimensional. Okay, so once you embrace the vector notation, then everything works out in high dimensions as well. So there you go. So the problem, you can see that the problem is probably not something that we can easily resolve, something like this. So how can you take the exponent of a matrix? Okay, so it would be nice if we were able to do it, and it is possible, they just probably won't have enough time to work it out. So having said that, also one thing to remember that we have been doing for a few days now, linear algebra, which means that everything is linear, straight lines remain straight lines. Okay, that's true. So linear algebra, all straight. Okay, so but let's not forget that the linearity of itself does not mean that our ODE will be made of straight lines. So not straight. Okay, because the derivative is linear does not in some way that in some sense doesn't mean that the function is going to be linear. And so once again, example in the one-dimensional case, the linear operator. Okay, this is a linear operator in dimension one, but the answer is the solution to the ODE is exponential, so it's not straight at all. So just a warning. We're going back to linear algebra. Okay. Okay, so the determinant of a matrix, what is it supposed to determine? This is what it's supposed to determine, a very basic question that we ask, and that is the function, the linear operator, is it one-to-one and one-to? So we have run into that a few times already. And so is there some kind of projection collapse present in our linear operator? How can we tell? And the answer is, it is determined by the determinant. Okay. So the answer is very simple. And once again, remember that it is nothing but four numbers. And once again, we do not care about, if you think about this metaphor for two planes, and then how can, once again, with the stretchy fabric here, and that's my linear operator. And then, so you ask yourself, how can it be, say, not one-to-one? Okay, so it is a stretchy fabric. Well, what does that mean? So is it one-to-one? How would such an operation that is being controlled fully by moving the planks? How can it be not one-to-one? So if you try to imagine that it's not one-to-one, because in stretchy fabric, the stretchy fabric, oops, the point about it won't fold. Okay, it's the stretchy fabric, so it doesn't matter what I do with the planks, it will still stay tight. Okay, so that's the metaphor we're using. So even though I might shrink it like this to bring the two planks closer to each other, nonetheless they will remain tight because it's stretchy fabric, stretchy whatever rubber sheet maybe. Okay, so which means that if it does not fold there, then how is it possible for us to have not one-to-one? How can we have not one-to-one? How is it possible for such a transformation to be not one-to-one? The fabric won't fold, no wrinkle. How can it be not one-to-one? Well, the answer is extreme, so on the extreme end, so what extreme thing can you do in order to produce a function that's not one-to-one? Once again, you are controlling the planks. What do you do with the planks to make this function not one-to-one? Talk about what one-to-one means. Everybody knows what one-to-one means.
You so much mean to that.
One-to-one meaning they are, okay, sorry. This picture, so this is my A. Okay, and so the problem is that this is not one-to-one, this is 2-1. Same output, two inputs. Okay, remember, and okay, somebody has to give me an example so we can continue on. An example, what is it, erase it. So an example of a function from calculus that's not one-to-one. What? X squared, right. Okay, it is, however, a non-linear function. So linear functions are all one-to-one in calculus. That would you remember, with the exception of constant function, which is not. But otherwise, this is the standard example of not one-to-one functions. X squared, absolute value, fourth power, sine, cosine, all of these functions are not one-to-one. So if we think in terms of transformations rather than formulas, well, first of all, yx squared is not one-to-one because 1 and -1 result in the same output. Okay, the input is different, but output is the same. That will not one-to-one. So in other words, if we were to think of transformation, that's why I mentioned the folding. Okay, when the line in the one-dimensional case or the plane in the two-dimensional case, when it folds, that's not one-to-one. And it will be 2-to-1 if it is folds once. Then that fold creates a two outputs, two inputs that lands on the same place. So they brought together like this. Okay, so but I said that you cannot, that the fabric remains tight, which means that it cannot fold, which means that the only source of a problem with being one-to-one is what? Use the planks. Okay, so unless planks themselves come together, there won't be any problem with one-to-one. Okay, so if they're not together, if they're apart like this, it doesn't matter how little room is left here, it will remain tight everywhere, and so it will remain one-to-one. So that's linearity for you. And then and so literally the two axes, two planes have to come together like this. Okay, so then the fabric will where will be the fabric? If the two planes come together, where's the fabric? Same place. Okay, so that's the extreme case because it has to be it is being held by the planks, and so if the planks come together, then so the fabrics also come together, and so it's not only function is not one-to-one, it's also not onto. Onto, remember another concept that we heavily rely on is whether or not the output is covered fully or not. So that's so if you were missing any values, x squared is now once again a good example of function that's not onto because negative numbers are not covered. Okay, so with linear functions, things way simpler on one hand, but because we're in the two-dimensional place, then things are not really that simple. But if we work them out, the answer does turn out to be simple if we just do the math. And that's the distinction is very important, because then if the function is one-to-one and onto, then the function exhibit very typical behaviors. And so it gives me my differential equation also will be behaving nicely. If it is not one-to-one, there would be behaviors, as we have seen, some kind of awkward looking. So we'll look into that later. We just we stick to the linear algebra for now. So then you ask yourself, then how is it possible to bring the planes together? What does that mean? It means that my basis vectors come together. And they come together, what does that mean? It means that they're multiples of each other. Okay, and so that's what creates a function that's not one-to-one, because we clearly, if two vectors come together, they're not. It's not one-to-one. But the point, if they are multiples of each other, then what happens is anything outside of this line is lost. You cannot cover it with the rest of your xy plane. So this is my xy plane, and we see where it lands on here you have maybe UV plane. Okay, UV plane. And we look at where on the UV plane, xy plane lands, and in which way. And ideally, it covers everything in a one-to-one fashion, or uniquely one sheet without pooling or anything like that. And then so that's how it cannot happen. So rotation is it, stretch is it. Remember that discussion. What else? A flip is also it, also one-to-one and onto. And when do we not have it? And then the answer is projection. A projection is a typical example of a not one-to-one function. But so let's go through the examples before we get to the determinant. So this is a function. So seemingly random matrix is chosen, but as you can see, vector 1, 0 stays. Okay, so what is the first column? It's where the first vector goes. So vector 1, 0, where does it go? It goes to itself. And then 0, 1, where does 0, 1 goes? It goes to 1, 1, and that's what the picture shows. So the two vectors that used to be perpendicular under the transformation, the second vector becomes 1, 1. And so you can guess, and the picture suggests, so that you can see what's happening. Well, it's not a rotation, obviously. It is, once again, remember what do we call this? Such a transformation. So what you can see what has happened to the ellipses. You think it could be a rotation, and we cannot really determine that, but also it could be shearing. Once again, remember the shearing. So I could actually shear this one into that. So it is actually, yeah, it is actually shearing, but nonetheless, it's not that we don't care about that right now. It's the behavior is generic, because the function is if you look at where the ellipses go, it suggests that my transformation is both one-to-one and onto, because these if you expand those, keep expanding those ellipses, they will cover the images of those ellipses on the right will also cover everything, and they never intersect, so everything is fine. The behavior is generic, and we know, how do we know that's the case? Because the two vectors are not multiples of each other. How do we know that? Look at the matrix, and these two, you cannot multiply 1, 0 by anything to get 1, 1. So that's the thing, and actually that's another way. A substitute for the determinant is just to look at whether or not the two columns are multiples of each other, because they are the vectors. So once again, the vector 1, 0 and 1, 1 are the two columns of my matrix. Okay, so that's always the case. Here's another example: 1, 2, 2, 4. 1, 2, 2, 4. What is so special about the two vectors 1, 2, and 2, 4? One vector, the other vector, any?
2 does double 1, 2.
Right, yeah, twice. The second is double. If you double the first one, you get the second. So and once again, these are where the basis vectors go, and so they go into the multiples of each other, which means what? Which means that there's this collapse, or as we usually call it, a projection. So as you can see, that's the first vector goes to 1, 0, to 1, 2, and the second one goes to 2, 4. They're parallel, which means that there's nothing else. So as you cannot see it here, but where did those circles go? And they're still within that line. So these circles say, if I take this green circle, where is it? It's here somewhere like this. So the circle over here, it's still there, but it's been collapsed into a segment. So we had an example like that before. So once again, that gives you an idea of what we're after if we want to determine whether or not my linear operator is generic. So once again, the word is pretty descriptive. Generic behavior, so one-to-one and onto, and our differential equation will be also kind of generic. And this is special or singular when there will be collapse. There are special directions. In that direction, there's a stretching in that direction possibly, and then there's a collapse in the perpendicular direction. So the difference between the two matrices is indeed the fact that there is a multiple relation between the two columns. In other words, for special is singular. So a matrix is called singular if its two columns are multiples of each other. Okay. So if we try to analyze what it means algebraically, that's what it means. It means that AC is equal to BD multiplied by some number X. Okay, X could be 0, by the way. So, and it doesn't matter what X is, it creates this relation between the two columns. It creates the relation between the two places where the basis vectors go. And therefore, if there is such an X, then we have a problem because the two vectors come together, and then there's a collapse. Okay, so then that's what we're going to examine now. Under what circumstances is a matrix? Let's jump pages forward. And the answer is that, so this is the algebra, and let's find out what it means. And it's really uncomplicated, because then A is the same multiple of B as C is a multiple of D. So that's what it says. So first of all, A is equal to XB, and secondly, C is XD. Okay, so then let's eliminate X from the equations, solving for X, substitute, or in this case, as you can see, I multiplied to make it more neat. I multiplied both equations. One equation I multiplied by D, and the second equation multiplied by C. So there's a cancellation on the right, because then there I have XBD on the right, and when I subtract, there's a cancellation. So that AD minus BC is the magic number that determines whether or not such an X exists, because think about that. If X exists, this works out. Okay, if X exists, this works. But only if it exists. If X does not exist, this does not work, because you cannot do algebra with something that doesn't exist. Okay, so even though we don't know what X is, but we imagine that such a thing exists, and then we can subtract X from X and get 0. If X does not exist, you may have noticed that in calculus, that if you try to do algebra with the limits that don't exist, then everything goes to hell. So that's a similar situation, but it has nothing to do with calculus really, but it's purely about, once again, you have to know that something exists in the first place before you do algebra with it. So once again, 1 over 0 minus 1 over 0, what's the answer? What?
Some fun. There's no such thing as undefined.
There is no such thing, but it's not, the answer is undefined. Each of the parts of the formula are undefined. So 1 over 0 doesn't exist, so you cannot subtract something that doesn't exist in the first place. Okay, so it doesn't matter what you might think 1 over 0 is, if it's you cannot, there will be no cancellation. So even though there are two identical things next to each other, you cannot subtract them, and you expect to have a 0 there. So in a similar idea applies here. So if X does not exist, this thing breaks apart. And but if it does, it doesn't matter what it is. Everything works out, and then turns out to that the fact that if we assume that there's the two columns are multiples of each other of our matrix, then it turns out that AD minus BC is equal to 0, and that AD minus BC is called the the determinant, because it does determine whether or not the matrix is singular or not. Okay, so as you can see, it's kind of weird multiplication diagonally, AT, but by the main diagonal minus the product of the other diagonal. One and only thing that we have seen in linear algebra that actually is not linear, but because it involves multiplication, and it is a very simple, ultimately it's a very simple computation, becomes really complicated once you go to high dimensions. But in dimension 2, it is literally what easy to remember, just cross multiplication and subtract. Okay, so what it determines is this. So 2 by 2 matrix is singular if and only if its determinant is equal to 0. Okay. And moreover, which is what we care about the most, is that function of matrix is 1-to-1 and onto if and only if the determinant is not equal to 0. So determinant is equal to 0 creates a relation between the columns, and that's a bad thing. So remember, I'm not sure how that much that comes up, but 1-to-1 is good. It's a nice function. Onto is a good function once again. So if the both of them is really good, and so it turns out that one single number will determine whether or not a linear operator is 1-to-1 and onto. So determinant determines when it is 0 is bad. Okay, so when it's not equal to 0, then we're good. There's something happening, but nothing special. So we will overlap with XY plane, overlapped over the unit plane with possible rotation stretches, but there are no collapses. Projection, that's the collapse that I'm referring to. The technical word is projection. Okay, so literally draw a line on the plane and then push everything. Not push, but the collapse is a good word because it's not a shrink. If you shrink by a factor of 2 or by a factor of 100, it still remains infinite. What happens is literally it kind of snaps into a line. The plane snaps into a line, if you can imagine that. Like an infinite roll around it, and then that's where determinant is equal to 0. Okay, so suppose A is a 2 by 2 matrix. Determinant is not equal to 0 if and only if the solution set consists of only 0. That's another way to interpret the same thing. So we forget about the linear operators, but look at make an equation from it. X is equal to 0. So we look at what values of x under A go into 0, and the answer is maybe none. Well, it's never none, because remember, A0 is equal to 0, so it's never none. But are there any others? Okay, if there are others, then that's what here. That's what happens now. There's a whole line of things that hit 0. So if this is 0. The projection is this whole line right here. This is the whole line. This one goes to 0. Okay, so that's what projection is. The whole line goes to 0. So is there or not another x that goes to 0? If that's the case, then not only that point goes to 0, but also the whole line goes to 0, and then definitely the function is not 1-to-1 or onto, so it's the matrix is singular, and as you can see, that is determined by that little fact that determinant is equal to or is not equal to 0. Okay. So that's the why determinant is introduced in the first place. So once again, separate generic behavior from non-generic and kind of a dramatic behavior where things, crumble in some way, collapse or crumble like this. So there are others. It is very convenient operation. So if we just look at the determinants for the basic operations that we have. So the 0 operator determinant is equal to 0. Okay. The identity operator, the determinant is equal to 1. Okay. So clearly already it's working out. The identity operator does nothing, and so its determinant is not equal to 0. So everything is fine. Okay. The flip about the y-axis. The matrix is -1, 0, 0, 1, but the determinant is -1. So as you can see, there is a difference between the identity operator and the flip. Okay, so that's negative sign indicates something and indicates the flip. Okay, so that's the determinant catches that, even though remember the matrix is made of 4 numbers. Determinant is one single number, but certain things it does catch. And so as you can see, it catches one, not, well, is it or not one-to-one onto, but also some other things that are not really related, such as -1 versus -1. That's the difference. Do we flip or do we, is there flip? There may be many things happening, but is there among those things a flip? And so as you can see, in this case, it is a flip, so it is -1. The flip over the x-axis, remember, okay, so that's an exercise. Okay, what are the, what's the matrix of the flip above the x-axis? One, zero, zero, -1, correct? And my determinant is 1, -1 minus 0 times 0, so it's equal to -1 again. Okay, so two flips. That's the similarity between them. So I cannot tell the part. So it's the same, which is a bad news in a way. So the determinant will not tell the one flip from the other, but it does detect a flip. Okay, so that's the good news. Flip about over the x-axis followed by flip about the y-axis. Look at it. So the double flip, the central symmetry, has two minus signs. Okay, on the main diagonal. The chart is 1. What does it tell you? There is no flip. I mean, two flips cancel each other out. One flip and then upside down and do one other flip, and I'm back. That doesn't matter which way, literally, I take one flip and the second flip is this. But nonetheless, what the screen was up, it's still up. Okay, so that's what the two flips mean. Of course, it doesn't matter what that may be a bad example. It's one example of why the flip matters, and how many. So if it is an even number that it's out, it is when you flip, is what happens to this counterclockwise versus clockwise. So when you flip, it changes to the opposite. If you do it twice, you're back. So that's what happens to the orientation. Remember the circles, we had those circles, and after the transformation, we saw clearly that the circles are now circling in the opposite direction. So that's where there is a one flip present. One flip that is not canceled by another flip. Okay, so it is an important thing about both the linear algebra and calculus, because not everything is orientable. So some suspect that maybe the universe is not orientable, meaning that there is no distinction between left and right and clockwise and counterclockwise. So maybe you make a trip, and if you go far enough and come back, maybe you come back, you mirror image of yourself. No. Anyway, flip about the x-axis followed by flip about the y-axis. Yeah, so that's what it is. Okay. So positive sign is an indicator that there is no flip. The net effect is no flip. Okay, so central symmetry actually has no flip as such. Okay. Flip over. Flip about. What is it? Flip over the x-axis. Okay, so. Okay. Okay. Flip over the x-axis followed by the flip over the y-axis. Same thing, but incidentally, number 6. Over the x-axis, then y-axis, or it's the same thing. Okay, x-axis, the y-axis, then x-axis, that doesn't matter. Same thing, and once again, they cancel each other out. Okay, the stretch along the x-axis even disproportional. Okay, so suppose lambda and mu are two positive numbers, so we have stretch along the one axis this much, and the other axis that much. We already know what happens. Those circles become ellipses, kind of disproportionately stretched. And then look at the determinant, though. Determinant is what? What's so special about it?
Positive.
And it is, that's right, it is positive, so there is no flip. So naturally, as you would have guessed, that stretches do not create flips. Okay, so that's the point. But this is what they do. Okay, so as you can see here, is if you, what happens if there are two stretches, you could so what's this supposed to be? This is 2 and 2, and then the lambda and mu stretch in the both directions, doubling in both directions, producing the determinant equal to 4. Okay, so as you can see, if you have two stretches, lambda and mu, in the determinant, they get multiplied. So if I have 2 and 2, that's 4. Okay, that's good, but that does not tell us, if we try to walk backwards and try to, if the determinant is equal to 4, what does it tell us? It could be this, when it is 1 and 4, also determinant is equal to 4, right? Okay. So once again, in the horizontal direction by 2, in the vertical direction by 2, these lambda and mu are equal to 2 and 2 altogether. Determinant is equal to 4 according to the formula. And then you can also have the same effect, the same determinant of 4, if there is no stretching in the vertical direction. In the horizontal, you quadruple. Okay, so so what's the point? What do you detect? If the determinant is equal to 4, what information do you extract from that?
Just not for
What is being extracted by 4?
every value.
It is actually about the area.
Yeah, areas 4 times.
Right. It doesn't matter this way or that way. The area is quadruple. The area is quadruple. You can do it in a number of ways, in infinitely many ways, but what they do have in common is that the even though the stretches may be proportional, disproportional, that doesn't matter. 4, 1, 1, 4, right? I could go with 4 1s to say that. But the area of the unit circle has been unit square has been quadruple. That's what it is. And now, once we start going in that direction, we realize that what's the meaning of the negative number? Once again, of the negative determinant, it is stretched with a possible flip. So that unit square may have been flipped. And so once again, that's the negative sign. This is very nice. Also the rotation. Okay, so look, the computation of the determinant of the rotation turns out, look at it. Does it look familiar with this one? Sine squared plus sine squared is equal to 1. What do we call it? Anybody remembers the formula in the first place?
I can't remember what the name of that.
There is a name for it. Kind of a familiar. Anyone? Where the formula comes from?
Comes from Pythagorean
The
theorem.
Pythagorean theorem, so you can actually call it Pythagorean theorem, but it happens to have the hypotenuse equal to 1. That's all. So if the hypotenuse equal to 1, then the angle will produce cosine alpha, sine squared alpha. The other two sides are these, and then it is supposed to produce and then Pythagorean theorem is to produce 1, and then indeed determinant is equal to 1 for the rotation, determinant is equal to 1, so there is no flip. If we now to analyze this one, what do we conclude is that there is no flip, okay, number 1, and the second one. And the second one, no stretch. Okay, so that's what determinant of 1 is. The stretch, to be clear, not no stretch of area. So roughly, 1 by 1 square may be stretched, but the area will remain 1. That's best we can conclude, but it's pretty good. And there is no flip. So it is a rigid motion. So that's actually how one you can we haven't demonstrated that, but that's rigid motion. We'll always have determinant equal to 1. Projection gives you 0. Okay, so projection width, even if you have a stretch there thrown in, it will still produce the term equal to zero, so that's very nothing. So collapse means what? Even though it's not collapses to a point, right? So collapse could mean a collapses to a point or collapses to a neutral. And both of them produce zero and determined because the area, what happens to the area, in either case, one is more extreme than the other, but nonetheless, the area in either case becomes zero. So it used to be one, and now area is equal to one, and now area in either case is equal to zero. So that's how we know that there's a collapse there somewhere. Okay, so so once again, the interpretation of all that we have had can be interpreted in terms of this equation. X is equal to zero. Is there not one single answer? If there is, that's answer is zero. If there is another one, there is a collapse. That's literally what a collapse is. A of x is equal to zero. Think about, so some vector becomes zero. That's a collapse. And only zero is allowed to go to zero. If not, then we lose our kind of generic situation because of the collapse. So once again, determinants of the zero is only possible when that is the case. There is only one solution to our equation. So it's called a bijection, in case you remember that word. Bijection is 1 to 1 and on. Okay. So that's the picture you already saw. So is there a vector that goes to zero? And as you can see, what happens if there's only one vector, so x is taken to zero by zero, but then every multiple of that vector also goes to zero. So if we have one little vector here, x, okay, and then I take all the multiples of it, because of the linearity, k can be factored out. And so if a of x is equal to zero, the whole thing is equal to zero. Every k, no matter what k is, positive or negative, also goes to zero. So it produces a whole line of vectors that go to zero. So that line collapses to zero. So every line collapses, but this special one that collapses to zero specifically. So if a vector is taken to zero by a linear operator, then the whole line in the direction of that vector from the origin is taken to zero too. Okay, so that's what the picture shows. Okay, so so a good place to put a line here. So this is test. This is not. So there might be one problem possibly about the last section. So we have actually, so linear algebra will be on the test specifically as linear algebra, so without references to differential equations. That's been quite a lot of time doing it. So the whole thing, since for a while, was to translate the theory of differential equations into three-dimensional case into the language of vectors. Okay, so we are still on that. We stayed with that for a while. Okay, so all right, so that's determinant, very big thing. Determinant, anybody remembers determinant anywhere else in calculus, maybe? Cross product, yeah, but the simpler one is probably change of variables in integrals. In dimension more than one. Okay, so then you need to adjust when you change variables. Okay, so change the axes. Okay, so then if the new unit is bigger than the old ones, you have to have an adjustment coefficient here, so not to overcount or overmeasure, because in the same units the answer would be too big, and so that's where the area, how it happens to the area of the unit square is used as a adjusting coefficient, and that coefficient is determined. Remember, the determinant, once again, what it is, one way to interpret it is the a rescaling of the area. Here, rescaling of the area. Yeah, so rescaling coefficient. Rescaling of the area coefficient. So not the separate directions axis, for example, but combined direction. So you look at the area, and naturally in dimension 3, it will be the volume, right? 3 dimensions. So whatever happens to the cube, okay, whatever happens to the cube, that will be the determinant 3-dimensional matrix. 3-dimensional determinant will have the scaling coefficient of the cube. And once again, if you do integration, that would be determined to come up. Okay, so all right, so the different angles that we take is this. So once again, this is a familiar picture, and that's once again how the matrix is formed. From where we are able to our axes, axis is not, so thinking in terms of transforming axis is a little bit misleading because you wouldn't notice rescaling of that axis. So the axis will look exactly the same as before, but it may have been stretched. So that's why we prefer in linear algebra to speak in terms of vectors. Okay, so the vector is what happens to the vectors. You can see the green vector has become longer, and that is crucial because then the fabric that lies between the two here, then it also has been stretched in that direction more than in the other direction. Okay, so the stretching is along the axis becomes very crucial, and that's written this way. So we ask the question: are there special direction along which there is no rotation, but there is only a stretching? Okay, so that's what this equation says. This here in the box is vector is given. Okay, so well let's write. And then it's possible that there is a stretch in a particular direction and not in the other. So rotation, for example, has no stretching. Every vector rotates. Okay, so every vector is not a multiple of itself. But if you do stretching, you do flipping, flips. What's the meaning of the flip? You just make it negative, right? So that counts. So let's look at some of the examples. So if my matrix is 2, 0, 0, 3, we know that it's 2 stretches, and then we ask ourselves what happens to are there any vectors? But because it is disproportional, okay, because it is proportional, that there is simplistic description of stretch by 2. So that's, if you want to read it from here, it is stretched by 2 horizontally, stretched by 3 vertically. That's simplistic. Even though that's exactly what we do, and that's exactly what we see on the picture, it ignores what happens in the middle. What happens in the middle? So there will be some stretching by what factor? We don't know, it depends. And then if you try to, because we describe the whole thing in terms of stretching, you will be tempted to also describe the rest of the apparatus as stretching, but it's not the case. Remember, they actually, there's my picture here, but they also rotate. So diagonals rotate. Okay, so at a different degree. So because the stretch in one direction is different than in the other, the diagonal direction will be not only stretched by some factor, but also it will change the angle. Okay, so that's what this proportional is. If it was proportional, then it blows up in all directions at the same rate, and so everybody is multiple of itself. But here it is, if we ignore the rest of and we choose the simplistic description, then we might forget what's happening with the rest of the vectors, and they are not multiples of each other. So if you don't believe me, say take a vector 1, 1. So 2, 0, 0, 3, I multiply by 1, 1. What do I get? I get 2 and 3. Right? So 1, 1, 1, 1 goes to 2, 3. It's not a multiple. So the stretch, because of the disproportional stretching, the angle also changes. So it was 45 degrees and now 2 3s, so it's kind of a down a little bit. No, up. No. So it was like this 1, 1, right? And then under the transformation, it looks a little bit like this. So it is 2 3. Okay, so that's the rotation. It's not literal rotation because the vector is rotated, but the a linear operator is not a rotation. Rotation is a linear operator, it rotates the whole thing uniformly, but if anything else is happening, then just some of the vectors have been rotated at a different degrees depending on where they are. Okay, so that's what we see. Once again, you could try to think what happens, and then there are two stretches, and everything works out fine. But the what is hidden here, that's what's hidden. The intermediate vectors. So once again, if I try to draw this vector, then it becomes this one, and then it becomes possibly that one. Okay, so that's what happened on the two transformation in a row. So just like I said, 2, 3 is not equal to any multiples of 1, 1. So there are two special vectors that are being stretched. These are the special ones. Okay, and this is generic really. All the vectors behave this way, not that way. So if we start stretching along other axes, that's even more hidden. Where is it a stretch? You can't be sure that what's happening here because if you don't know ahead of time that it's a stretch along other axes, you might think about rotations more than anything. But it is actually two consecutive rotations like this. Yeah, that's it. So you could try to see where maybe. Yeah, once again, if I go diagonal like this, so then this is where it is. Okay, so 1, 1 over here, 1, 1 becomes 1, 2. That's right. Possibly. No, not. It's not 1, 1 actually, but it is diagonal then. It's like 1/2, 1/2 or something like that. So there are no numbers here. But you can see that once again, disproportional stretch in this case, it is not along the main axes, and so then you cannot even predict what. Look at the effect. There's clearly a rotation over here. At least the axes of the ellipses are aligned with the axes of the xy plane, and here they're not aligned anymore. So my circle become ellipses, but where does that axis of the new ellipses come from? They are ellipses, and clearly I can tell that the axis of the ellipses, but other than that, you cannot tell. So, and that's where it comes from. So when the stretching is aligned or misaligned with the axis, the effect might be different. It doesn't matter, and that's really what we care about a lot is that we don't really want to be married to the axis. They can change, so we can choose different bases, and therefore the stretches will be less detectable. And so how do we detect those special directions? And the answer is well, there's a fairly simple algebra behind it. This is another example. So algebra is coming up. So disproportional horizontal vertical stretching, as you can see, and once again, if you zoom in on it, you can see how this. You can see the arrows are close to each other on the left and on the right. That's the stretching, and indeed you can see that stretching by 2 in the horizontal direction and by 4 in the vertical direction. And every other one has been rotated. Like the brown one rotated, the green one rotated a little bit, and then they will rotate every one, but less and less. Okay, so that's what it does. And indeed, the only these are once again the special one, but these are the generic ones. So special, and these are generic. Generic meaning that they behave in a manner that is not uncommon. So they fanned out. Okay, so they kind of almost random behavior, and the two directions are special. So they called eigenvectors. Okay, so eigenvalue is the coefficient. Eigenvector is that vector that being stretched by the operator. So every operator has hypothetically eigenvectors. Own means own in German. Eigen. Okay. Own or characteristic, which is pretty much the same. in that sense. So I don't know any German, but that's at least how it is translated. So it is something inside of the operator that behaves in a very specific way, in a manner that is really, really simple. So well, the operator behaves in some very complex way, possibly, but there are certain directions along which nothing special is happening. So the direction, they do not change the direction. Okay, so once again, this, as you can see here, these two directions are steady, and in fact, the two axes are intact, where they stretch, but they do not change direction. So that's what we're after. And so the idea is, if we find these special directions, it will supposed to tell us a lot about what the operator does and how. Okay, so let's take a quick look. So that's the definition. So literally, A of B is equal to lambda B, what lambda is. So let's take a quick look at the simple examples of eigenvectors, eigenvalues. So I take the matrix. I'm doing it in a brute force way. So lambda B is equal to IB. I is the operator, which is I of B is equal to B. So which means that I end up with an equation lambda B is equal to B. So lambda, the only way for it to happen is lambda is equal to 1. Okay, so there's only one eigenvalue, but it applies to every single vector. 0 doesn't count, as we can see here. Remember that the exception is that has got to be non-zero. Okay, so that's literally what it is. Lambda equal to 1, that there is nothing that's happening to none of the vectors. Every vector stays. Okay, 2, 3, as we just discussed. So once again, so let's go through the let's go over its computation quickly. So we already know the answer. That's why it is 8. So we know that 2 and 3 are stretching in the horizontal vertical directions, and nothing else happens elsewhere. We already know the answer. So let's go to algebra to rediscover that. Okay, so we write our equation. That's our definition of an eigenvector. And so we're looking for 3 things at the same time. We're looking for V, 2 numbers, and lambda, the 3rd number. So we're looking for 3 numbers for one single equation. It works out somehow. Okay, so we're looking at 2, 2, 0, 0, 3 matrix multiplied by xy, unknown xy that we want to find, equal to lambda xy, and lambda is also unknown. Okay, so let's just break it into components separately, and we'll see what happens. Okay, so I carry out the multiplication on the right, and on the left, I end up with right here. I end up with 2x 3y, and then it's supposed to be equal to lambda x lambda y on the right. Okay, I break it apart into components right here. 2x is equal to lambda x, 3y is equal to lambda y. If you look at it, what the way it looks, it is actually impossible. Right? Look at it. Lambda, you cannot have simultaneously x, well, you could, you have 2 candidates right away. Lambda is equal to 2 or lambda equal to 3. To be careful, however, this is the way we do it. We bring everything to one side and factor. Okay, so then I have x times 2 minus lambda, and I have y 3 minus lambda. So once you have that, you realize that you cannot have you cannot have both of these at the same time for lambda, because either lambda is equal to 2 or lambda is equal to 3. It cannot have to be simultaneously 2 entering. So which means that what's the answer? How do we continue on with this? So this is the equation, okay, the system of equations. And once again, you cannot have lambda simultaneously be equal to 2 and 3. How is it possible then?
Set them.
What?
Set them equal to each other.
No. What's the meaning of x and y? Well, what is the role of x and y in this equation? If one of them is 0, then yes. So exactly. So for example, if lambda is equal to 2, then the first equation is equal to 0 automatically, but the second one is not, unless y is equal to 0. And vice versa. If lambda is equal to 3, the second equation is 0, done. But the first one is not, because 2 minus 3 is -1, so x must be equal to 0. So by that logic, we will produce one value of x and one value of y for 2 different values of lambda. So unfortunately, there's more than 1 and typically 2 different values of lambda. So that's the conclusion just made. The only way for the first equation to be satisfied, that is either x is equal to 0 or lambda is equal to 2. And for the second one, y is equal to 0 or lambda is equal to 3. And so that, what does it create? It creates two eigenvectors with two different eigenvalues. So lambda could be 2 or 3, and the vectors are, well, it doesn't matter what in the first case is. It is the only thing that required here is that that x is equal to 0. So any vector 0y works. Okay, 0y meaning the vertical vector. And for the second one, x 0 works. That's the horizontal vector. So as long as lambda is equal to 2, every vertical vector will do. And if lambda is equal to 3, every horizontal vector. Okay, so that literally produces a bunch of, it gave us the eigenvalues 2 and 3, okay? But it also gave us vectors, a bunch of eigenvectors. So if I were to combine these, this is what we have as a result. Lambda is equal to 2 horizontal vectors, vertical vectors. Lambda is equal to 3 vertical vectors. Okay, so indeed that we are rediscovering what we already knew from by design, that the horizontal vertical stretching and nothing else is being stretched, just stretched. Every other vector is not only stretched but also rotated. So we are not interested in that because their behavior is not as regular as this. So to summarize once again, x any y is equal to 0, the vector is x 0, and under multiplication you can easily verify the vector doubled. So along the x-axis, everything is doubled. Along the y-axis, everything is tripled. And so that is the answer. Okay, so we'll just have to pick up where we stopped. That's right. I'll see you next week.